Welcome to a lecture on the forced vibration of a single degree of freedom system. Uh, so far, we have discussed the free vibrations of a single degree of freedom system. We discussed the free vibration under viscous damping and Coulomb damping. So, in free vibrations, we did not apply a force continuously on the system, but we just gave some initial disturbance to the system and left the system to vibrate, and the system vibrated with its own natural frequency. In case of forced vibration, when we say forced, means there is a force applied to the system, and what will be the response of the system, what will be the frequency of vibration of the system in this condition. So this will be the subject of this lecture. So let's discuss the type of forcing functions. So what are different type of forces that are loads that can be applied to a system? So the force could be very simple, is harmonic one. So already we have discussed what is harmonic motion. So similarly there is harmonic force like F0 sin omega t or F0 cos omega t. They have fixed some constant frequency, they have constant amplitude. Then another type of force could be periodic force, as periodic force is also have some constant interval after which it repeats. And from Fourier series we know that a periodic function can be represented in terms of harmonic series. So the third type of force could be impulse force or some step function, some impulsive function. So in a very short duration of time, a very high amplitude of force could be applied, and this force function is called impulse. Then the last that force we discuss is the random one. So there could be a random force on the system, like the force of the wind or some earthquake. They are random. So these are the mainly four type of forces, but out of this we are going to concentrate on the harmonic force. So we have a single degree of freedom system that comprise mass element, stiffness element and damping element, and we apply this harmonic force like F0 sin omega t. So with time it is sine curve, and at each instant of time it is working on the system, acting on the system and varying as a sine curve with time. So when this kind of force is applied, what will be the response of the system? That is the important point of investigation, how the system will behave. Because if we see in case of free vibration, the system was vibrating. When there was undamped, it was vibrating with its own natural frequency. When it was viscous damped, it was vibrating with some damped frequency, that was omega d equal to omega n root 1 minus zeta square. In case of Coulomb damping, free vibration case, it was again vibrating with omega n. But when we have the forced condition, then what will be the frequency of vibration? what will be the amplitude of vibration? Means the amplitude of the response of the system. These are the important aspects to study. So let's make again, we will follow the similar analysis procedure that we discussed in the previous lectures. That okay, we have a system, we isolate the system, make free body diagram, show all the internal and external forces and inertia forces, and we apply Newton's law of motion or D'Alembert principles, and we find the differential equations representing the equation of motion of that system, and then we go for the solution of this system, and the solution will give us the response of the system, and based on the response we can get some insight into the characteristics of the system. Okay, so we follow the procedure, same procedure. So we have a single degree of freedom system. It has only 1 degree of freedom in this direction, the vertical direction we can say, and here is a force applied on this system F, that is harmonic. So it is F0 sine omega t, and we know that this system has a natural frequency omega n, that is root k by m. So we make free body diagram of this system. So this is our mass. So to make a free body diagram we have to, let's assume that when this system is vibrating under the application of this force, and at a particular instant of time t, it is at certain displaced position x. So here let's say here it is at some position x. So when this is displaced at some position x, there is some spring force working upward, that is kx, and it has certain velocity with respect to the damper. So here we will have some damper force c x dot, and already here this force F is acting F0 sine omega t, and we assume the direction of acceleration and x here in the positive direction. So this is the free body diagram. We showed these forces, and now we will apply the Newton's law of motion. So Newton's law, we said that sigma F equal to mx double dot. Okay, so this is the Newton's law, and so mx double dot equal to, so forces are spring force and that is acting opposite to x double dot direction, so it is minus kx. Then there is a damping force that is again acting opposite, so cx dot, and there is this force, it is in the direction of this acceleration, so f0 sine omega t. So here we write mx double dot plus cx dot plus kx equal to f0 sine omega t. So this equation 1 is representing the equation of motion of the single degree of freedom system under forced condition. Now we have to solve this differential equation. So earlier differential equations that we solved, In the right side it was 0 because they were the free vibration case. Here again if we put F0 is 0, so it will be a free vibration, so if there is no any force, then to solve this kind of system, okay, we have the forced vibration case, we have the solution that will comprise the two parts. The theory of differential equations says that this kind of system will have the solution. So the complete solution will comprise two parts. So x equal to xc plus xp. So x is the complementary function and this is particular integral solution. Okay, so these two solutions will add up and give the complete solution of this system. So this, to get the complementary function solution, we will have this side will be 0, so we will have mx double dot plus cx dot plus kx equal to 0. So this is the case of free vibration, and already we have got the response of this system. So we already got that this kind of system has the response like a2 e power minus zeta omega n t, assuming underdamped system, minus zeta omega n t into sine. Here we have omega d, or we write 1 minus zeta square omega n t plus phi 2. So this is the response of an underdamped system. We have already got this in the free vibration. So xc is this one. Now we have to find xp. So to find xp, let's use some general sense and vector method. So the general sense says that to find xp we have this m xp double dot plus c x dot p plus k x p equal to f0 sine omega t. So this equation we have to solve, and the physics says that if we have a forced harmonic force acting on a system that has a frequency omega, the system will vibrate with the same forced frequency. So it means the response xp, first thing, it will also be harmonic, so it will be harmonic sine omega t, and here it will be x because here it is force amplitude, here will be some displacement amplitude, and it will also, the response will also be of the same frequency omega, but some phase lag, because we apply first the force and then the response will come later. After the response is the result of the application of the force, so there will be certain phase lag between the force and the response. So response will lag the force, let's say omega t, so minus phi. Okay, so the response is this is the, we assume this is the solution of this equation. So now we have to find x, we have to find phi if we want the solution of this equation. Okay. So now here we will use the vector method. So vector method, first we put in this equation. So this is equation 1. In fact, this complementary function solution, this is also, this gives the transient part, transient solution, transient response, and this particular integral solution gives the steady state response, steady state response. So now we have equation 1, let's say this is equation 2, this is equation 3, 4, this is equation 5, this is equation 6. Now we have xp, we calculate xp dot and we calculate xp double dot, and we put these values in this equation 5. So xp dot equal to x cos omega t minus phi into omega, because here is omega. So this we can also write omega x sin omega t minus phi plus pi by 2, because sin theta plus pi by 2 is cos theta. Similarly, we get to get xp double dot, we have to differentiate this. So we have we differentiating this. So we get omega square x, and this is minus sin omega t minus phi, because differentiation of cos is minus sin, and 1 omega again coming to square this, so it is omega square, and because this is minus, we can write this in another form like omega square x sin omega t minus phi plus pi, because sin theta plus pi is equal to sin theta. So we have these three terms. Now we put these terms in this expression number 5. So if we are putting this in expression number 5, so here is m xp double dot here m omega square x sin omega t minus phi plus pi plus c xp dot plus c xp dot is omega x sin omega t minus phi plus pi by 2 plus k xp plus k xp is x sin omega t minus phi, and this is equal to f0 sin omega t. Now we arrange these terms, and if we arrange these terms, we can write f0 sin omega t minus kx sin omega t minus phi minus c omega x sin omega t minus phi plus pi by 2 minus m omega square x sin omega t minus phi plus pi equal to 0. So this equation, let's say equation 7, this equation is of quite importance, because this equation is showing us four terms, and they four are the force terms, they are the forces. For example, here F0 sine omega t, this is showing the impressed force or externally applied force. Then kx sine omega t minus phi, it is showing the spring force. Then c omega x sine omega t minus phi plus pi by 2, this is showing the damping force, damping force. And then m omega square x sine omega t minus phi plus pi, this is showing the inertia force. So these four forces together are making zero, means they are in equilibrium. That is the D'Alembert principle. So these four forces we can represent on a vector diagram, because they are forces, they are vectors, we can represent them on a vector diagram. So let's make the vector diagram. So when we want to make the vector diagram, first we plot the x, the direction of x. First we plot f0, because f0 is sine omega t. So from here it is omega t. This is the reference axis. So it is omega t f0. Then phase lag of phi, we plot x, because x is lagging with phi here. Now we have to plot the spring force, because here f0 sine omega t minus kx. So minus of this x means it is opposite to the direction of x. So x direction is this, it is parallel to x direction and opposite. So this is coming from here, it is a spring force. So it is this kx, and its phase is omega t minus phi, because this is phi. Now we have the damping force c omega x sine omega t minus phi plus pi by 2. So from x it is making angle this minus pi by 2 lag. So from here it is pi by 2. So from kx it is plus pi by 2. So we have this. So this is c omega x. Then m omega square x, that is plus pi here with respect to kx. So it is like this. So m omega square x. And so the vector force diagram start from 0 here, from this and going this, and it is going to close. So these four forces are in equilibrium. Now we can write these. So we can make this vector diagram even better, like so we have x. This is f0. So we can write like this is kx and this is m omega square. So this quantity is kx minus m omega square x, and this is c omega x. So here we can write f0 square equal to kx minus m omega square x square plus c omega x square. So here we can write k minus m omega square whole square plus c omega whole square x square equal to f0 square. So here we can write x equal to f0 upon k minus m omega square whole square plus c omega square, and this is under root. Moreover, here we can also write tan phi equal to c omega x upon k x minus m omega square x, that is equal to c omega upon k minus m omega square. Okay. So we have got x, we have got phi, because phi equal to tan inverse this. So the complete solution x equal to xc plus xp, that is equal to a2 e power minus zeta omega nt sine root 1 minus zeta square omega nt plus phi 2 plus xp. So here xp is x sine omega t minus phi, and x is given by this equation. So it is f0 upon k minus m omega square whole square plus c omega whole square under root. So this is x into sine omega t minus phi. So this is the complete solution, and we see that this part is exponentially decaying. So this is the transient part, this is transient part, and this will decay after certain time, certain small instant of time, and this part is a harmonic function with sine function, and this is a steady state part, and this part will prevail even after this part is 0. So we can show the response of single degree of freedom system. So here we see that the first part is showing the complementary function xc or xh here is it. So it is going to decay with time. So here it is like free vibration, so it is going to decay with time, and this is the particular integral part that is harmonic sinusoidal, so it is continue with time, and the resultant response, the total response, complete response is the superposition of the two. So we superimpose the two and we see that initially due to the this transient part the waveform is distorted, but when the transient part becomes 0, the response completely is the harmonic response and with the same frequency as the force frequency, and therefore it is the steady state part of the response. So the total response is this one. So we understand that in case of the forced vibration of a single degree of freedom system, the complete solution comprise the two parts, the transient and steady state part, and the transient part will decay after some initial instant of time, and the steady state part, that is the harmonic with the same frequency as the forced frequency, will prevail for the rest amount of time. And here we derived the amplitude x of the response and the phase phi of the steady state response. So thank you for attending this lecture, and see you in the next lecture. Thank you.